It's actually a great pleasure and, in fact, an honor to be able to introduce Vint Cerf to you today. Before I do, I do want to thank Bobby Yanucci and Osman Yagan, who are responsible for making this happen, for the logistics and for inviting Vint in the first place. I just get to make the introduction. So I don't want to use Vint's time. I mean, if I were to spend the time listing his credentials and listing his honors, we'd be here a very, very long time.
They can Google that.
Right? They can Google that. And you see, but Vint is a recipient of the Presidential Medal of Freedom, and those are hard to come by. Turing Award winner, and a long, long list of other things. But really, you know, when we have these discussions about net neutrality, you have to go back and see that Vint is an author of many of the documents, the RFCs that went out in the 1970s that made the internet what it is today. And so it's very rare that we have the opportunity to meet someone who has been so influential in changing the world and the way in which we all live and work today. So it's really my pleasure to introduce Vint Cerf.
Thank you very much. You know, you really shouldn't clap before anybody has said something, because it makes you want to sit down. It won't get any better than that. So I sort of feel like the talking dinosaur. You know, it doesn't matter what I say. What's amazing is I can still talk. So I decided I wanted to cover two topics today. One of them is digital vellum, which is a question about preserving digital information over long periods of time. And I'm going to tag on to the end of that a little bit about the interplanetary internet and where we are on that. Some of you may have heard about that one already. I'm sure Bill has. But I wanted to bring you up to date on where we are and what our aspirations are. But the other thing I need to confess to you is that I am stealing some content from Satyanaran. I never get this right. It's Mahadev Satyanarayanan, who is a CMU professor. See, I did that pretty well. I've been practicing all morning. Satya has done some spectacularly good work at CMU on digital preservation. I'm going to show you what I understand of what he's done. I will not do justice to it. He may even be there watching this, in which case he'll get after me the next time we meet, which is later in the week. So what I want to emphasize is that I'm carrying coals to Newcastle in some respects, because the most spectacular thing that I have seen in the recent past on this question of digital preservation has come from Carnegie Mellon. So let's start out just with some of the motivations behind all this. We have had for literally thousands of years the ability to preserve written content in various ways. Sometimes it's on baked clay tablets. Sometimes they weren't intended to be baked, but there was this fire. And the problem, of course, is that even though you preserve the symbols, you may not be able to make sense of what they mean unless you know the language. But nonetheless, the bits, so to speak, have been preserved. And the same could be said for cuneiform tablets and for vellum manuscripts and papyrus and things of that sort. So there is this interesting question about other stuff which is now digital in nature, and which static is a little funny thing to say about a video, but in a sense it's a fixed format, right? It's just a series of still images. And the same would be true for pictures and things like that. So we have this historical ability to preserve content, and we have current ability to store digital content that isn't necessarily dynamic. I want to give you the motivation behind my interest in digital preservation, and it's this story about Doris Kearns Goodwin, who wrote this book called A Team of Rivals, which is all about Lincoln hiring the people that competed with him for the presidency. So he formed this cabinet of people who were competitors. But what's interesting is what Doris Kearns Goodwin had to do in order to write the book. The book reproduces dialogue of the time. And it really feels quite realistic. And the question is, how did she do that? Because she obviously was not there in the 1860s. Well, in order to do what she did for this book, she went to 100 libraries. I don't know what the actual number is, but a lot of libraries, in order to read the letters that were exchanged by the principals of that time. Therefore, she knew what they were talking about, what their positions were, and how they expressed themselves. And so the book reproduces a lot of this dialogue in that historical setting. Imagine that you're Doris Kearns Goodwin and it's the 22nd century and you're going to write stories about what went on in the 21st century, let's say in the first 2 decades. The question is, what resources would this 22nd century Doris Kearns Goodwin have? And the answer is not very clear. The emails, the tweets, and all the other things that we take for granted today may have evaporated into thin air because nobody preserved them. And so there's an open question in my mind about our place, our society's place in history, since we're so heavily dependent or increasingly dependent on digital content, and yet we don't have a regime that preserves it. Now, the internet has a very odd property. It preserves stuff you wish it would forget, and it remembers, so it remembers things you wish it would forget, and it forgets things you wish it would remember. And so we don't have a regime that preserves digital content in any rational and, let's say, regular way. Of course, we're all very proud of ourselves about these digital media. The problem is that the readers for them don't necessarily last very long. I mean, I still have, maybe you do. I don't have any 8-inch long discs, but I have 5 1/4 inch and 3 1/2 inch, and some old cassettes, and of course DVDs and Blu-ray, and who knows what comes next. The problem is that the physical reading equipment may not last as long as the medium, and there's no guarantee the medium will last very long either. I mean, take one of these polycarbonate diskettes and ask yourself, how will it look or how well will it read 20 or 30 years from now? I remember extolling the virtues of these high-density drives once, and the librarian smiled at me wanly, walked into the stacks, came out with a 1,000-year-old Vellum manuscript, magnificently illustrated. And then she smiled at me and said, "And how long did you say your polycarbonate thingy was going to last?" So I sort of crawled out of the room at that point. So we don't do a very good job right now of hanging on to bits. And to make matters worse, it's not just the bits. The problem is the bits have to be interpreted somehow. Here's another way of saving bits. This is the inside of one of the Google data centers. There's a lot of bits in there, but I don't know how many of those bits will be left or how many Google data centers will be left 1,000 years from now. And so I worry about this whole process. And of course, there's all these other things that, I'm sorry if I didn't get your favorite logo up there. But the point is, we produce a lot of digital stuff. And we have devices that are also producing digital stuff. Often it's sensor things like that. There are refrigerators and picture frames and phones that look like phones, but they're voice over IP devices, and there's internet-enabled surfboards and all these other things that are becoming part of our Internet of Things environment, which is just beginning to blossom. So there'll be billions of those, and they too will produce bits that we may want to keep and may want to be able to understand a long time from now. And then the thing that Satya has introduced into the equation is, what about executable content? And it's not just games. I mean, if you think about it, a lot of other objects that are digital in form are meaningless unless you have the software that produced them to interpret them. So think of spreadsheets, think of complex documents. Those are all things that need software to correctly interpret them. And we don't have a standard way of hanging on to the software as well as the bits of these digital objects so that we can use them years and years later. So we have, as Satya says, we've got museums for hardware, but we don't have museums for software. And maybe we should. Well, there are some issues associated with trying to hang on to the software that correctly helps us interpret bits. And this is the key problem. If you don't have the software, you don't know what the bits mean. One problem is that the software may have intellectual property rights attached to it. And so you may not have any right to keep copies. You may have no ability to get source code. You may not be able to share a copy of even an executable with somebody else. You can't just necessarily take something that you got and paid money for and then put it up on a cloud server and say anybody who wants to can use it, because somebody will say to you, you can't do that, it's not part of the license. So I want you to think for just a moment about the idea that maybe preservation deserves a place at the copyright table, the same way that fair use does. In the fair use regime, you're allowed to reproduce things up to a certain amount and for certain purposes. We don't have a regime right now that talks about preservation rights. And I think we're going to need something like that, or we won't be able to save the software that we need to interpret bits over time. I'm concerned also about the conditions under which you lose access to software. For example, if a company goes bankrupt and just simply goes out of business, the software is no longer maintained, and you go through multiple versions of operating systems until someday the software that you bought doesn't work on any currently available operating system, or it doesn't work on any hardware that you can get your hands on. And so we see this future of dissipating ability to correctly run software, which used to serve us well, and which we've invested time in using to produce other digital objects. So there's a lot of opportunity cost lost here. So I've been thinking about ways to describe data, describe files of complex files of bits, describe software, describe machine architectures and things like that. And I had been thinking mostly about somehow being able to emulate the machines that we used when we were running these various pieces of software. And I was trying to figure out, gosh, can I create this digital file that I could sort of start pulling on and pull in the description of the computer, then pull in the operating system that goes with it, and then pull in the application software. And I didn't see any really good way to do that. So I've been struggling with this for a while. Meanwhile, Satya was actually doing something, and that's the OLIVE project at CMU. Can I ask whether any of you already know about the OLIVE project? Not too many hands? Oh, good, there. So that means if I get this messed up, you should jump up and say, no, 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 you got that wrong. Or Satya will do that if he happens to be listening. So this is actually a very spectacular, from my point of view, foray into solving the problem. It doesn't solve all of the problem, but it makes a big step in that direction. Now, one of the motivations that Satya has for preserving content and our ability to correctly interpret it is to reproduce scientific results. And this turns out to be pretty important because you can easily have scientific results which later, it turns out, were analyzed incorrectly because the software that was used to do the analysis had a flaw in it. And the examples he has here are some spreadsheets, for example, that some researcher used to produce a result, led to a conclusion, made some fairly important statements about it, and later somebody else discovered there was a bug in the spreadsheet, not just in the program, but actually down in the spreadsheet software itself, not just the equations that were being used, that reversed the results of this analysis. Well, he could not have done much about that if the problem had been detected 30 or 40 years later, because the software wouldn't be available to analyze. Fortunately, this problem happened at a time when the software was actually still around and could be analyzed. But you can imagine over periods of time wanting to reanalyze software-based or data based on new kinds of theories that have come along. So figuring out how to hang on to things so that we can validate stuff is important. Now, this was the example that it was an Excel spreadsheet that didn't work out. And this problem would not have been adequately detected and repaired unless the software had been preserved in some way. If you think about a lot of software that's increasingly being used to analyze data that's accumulated in the scientific domain, you can tell that if you don't preserve both the software and the data, later on you may not be able to reanalyze the data with new software or hand new data to the old software to see how the program would have analyzed new information. And this is very important for understanding in some deep way what the meaning is of the experiments that we carry out. So the question is, why is it so hard to hang on to the software? And Satya makes very good points about the fact that there's a whole lot of stuff that isn't stable. So the hardware keeps changing. Software versions come and go. The operating systems change. I mean, the idea that I am running this program on Windows X is not a stable statement, because the same software may have to run on many different versions of the operating system. The software may have to track and change to adapt to new versions of the operating system. And so, just to pick a concrete example, I mean, we could speak of, this is an Excel spreadsheet. But any instance is actually an Excel spreadsheet of a certain version running on top of either a Macintosh or a Microsoft Windows operating system. And so one of the questions is, exactly what should I be preserving? Because just hanging on to the latest version of the software doesn't necessarily mean you'll be able to run the old spreadsheets or the old PowerPoint or anything else. I don't know if any of you have ever tried to take a 1997 PowerPoint file and make it work with the current versions of PowerPoint, and this is not a gratuitous dig at Microsoft. It's just that the backward compatibility is not always possible to maintain. And you get both either amusing results or really annoying ones, like, you know, all your pictures are rotated 90 degrees, or other, you know, the fonts don't get preserved, or the colors keep changing. So our ability to reproduce this stuff is not stable unless we're able to capture the version of the hardware, version of the operating system, version of the application in some way so we can reproduce the results. And he lists, I'm stealing Satya's slides here, but you can see all the other variables that need to be hung on to in order to reproduce the environment that the software ran in before. This is not a trivial exercise. So this is the brilliant solution that he came up with. Basically, he says, forget about the fact that the operating system is a thing, and the application is a thing, and the hardware is a thing, and we sort of treat them as separate. You know, we load the operating system, we boot up, then we load the application, then we load in the data, and we interact with it. What he says is, wait a minute, at the point where you're interacting with the data, you've got the application running and the operating system running, take a picture of that, capture all the bits associated with the state of that machine, and hang on to that ensemble. And then build a virtual machine on anything that, you know, that's capable of emulating the machine that you ran this stuff on. Build a virtual machine and just place the snapshot into that virtual machine. And it's now in the state that it was in when you were running it 20 years or 30 years or 50 years ago. And I think this is a brilliant recognition of the utility of virtual machines, first of all. And second, of the ability to take a virtual machine and to slam it into a particular state without going through all the boot up process and everything else. It's actually a really interesting tactic. And I accept the possibility that, you know, there'll be cases where this didn't work. But I will argue that it covers enough cases to be really interesting and useful. Now, he says that making virtual machines is not exactly trivial either. For one thing, when you think about running a virtual machine, it's going to be pulling out of virtual memory in various ways depending on the operating system and the application and the data that it's running. And so if you don't have enough room to store everything in real memory, you're going to start running into paging kinds of problems and everything else. And he's been trying to figure out how to do this not only on a local machine that's right next to you, but also in a cloud environment. And so what makes this very interesting is that you may run into the same kind of operational problems that we used to run into in time-sharing machines when they didn't have enough real memory, and they had to pull pages in from a disk drive, for example, and ended up spending most of their time just moving pages in and out of the machine, thrashing, in effect. So he's saying that he's going to figure out how to organize the state of the machine so that he can make it run even when it has to be pulling in data from some other place, in particular in a cloud environment. So he's done some very, very nice work making virtual machines function even if you couldn't store all of the state all at once in random access memory. So this is the structure of the virtual machine that he builds. Now, again, I'm not the expert, and so I can only give you my impressions of what Satya has done. But it's like pretty much any other kind of environment where you build the description of the machine that you want to emulate, and you let the underlying hardware carry out that function on top of that virtual machine. And then you load the operating system and the application and the data as well. Now, you could think right away of some constraints that this idea might place on you. For one thing, if this is a game that you were running, and pick your favorite game. It ran on an Xbox, whatever it was. It had this funny little interface gadget with 75 buttons on it. If the 75 buttons aren't available, or you don't know how to interface that 75 button game playing gadget into your emulated environment, that may not work very well. So there are cases where this doesn't work. But there are lots of other cases where this should work very well. And I think that's the key to his success so far. So let's see, he's running Linux, he runs the virtual machine, then he runs Windows on it, in this particular instance, then he runs the application on top of that. Then he runs a client that lets you interact with this environment that he's established. And then he goes off to a server. So he's trying to do as much as possible in the machine that's running the virtual environment. And then he's able to use a pure web HTTP interface to get to the server. And that makes it easy to work not only locally, but also across the internet. And this is how he stores the instance of the description of the machine and everything else as a single file. So this was the thing I was trying to figure out how to do, where you pull on the bits and they slowly build up a description of the machine and the operating system. He's even managed to make this work in a cloud environment, which actually surprised me a lot, especially if it turns out that the cloud is doing all of the executions, but you still have to find out how to get stuff onto the screen so you can see what's going on. Now, does anybody remember something called X Windows? There was a gal, yeah, and you remember that Judy Estrin did network computing devices, which basically, this is an improvement over a VT100, green screen display. But the idea here is very similar. What you want to do is to move things into the display only as needed. And he's even figured out ways of staging that by doing prefetching of what should be available. By the way, these slides will be available. So can we do that? Yeah. So you can save a little bit of energy. So the idea here is to page the stuff in ahead of time in order to make the thing look like it's running in real time. Same kind of thing as a multi-level cache. And that's actually worked out really well for him. So that's basically where he is. And the pity here is that this project is coming to an end. I think the funding for it has largely been completed. And so I don't know of any plans to follow on. And my belief is that this is probably the most immediate way that we could start caching programs and data that need to be preserved over a long period of time. And I'd love to see a regular practice of that happening. But as you can see, there are intellectual property issues that have to be dealt with, and there are mechanical issues, and there's a question of how to sustain this museum. Because this isn't just a museum that you look at stuff. This is clearly going to be a place where you want to be able to download or execute old software. Now, there is a place here in the Bay Area that's trying to hang on to things, and that's the Internet Archive that Brewster Kahle is running. I don't know if any of you have actually been there, but he now, yes, and it's that incredible, what was it, a Christian Science church or something? Yeah, and what was astonishing is that it looked exactly like his logo, which is why he bought the building. Oh, I didn't know that. Okay, so you should really go. I mean, this is two things about this place that are made. Three things. First of all, it's a church, right? So I always thought internet was a religion anyway, so it sort of makes sense. And then the next thing is that he didn't remove the pews in the church. So the pews are still there. It's just that where the altar would be, it's all the computers and the memory and everything else, you know. So you get this very strange atmosphere. And on top of all that, he has mannequins that are sitting in the pews. And, you know, they're dressed in various odd ways, as you would expect in the San Francisco area. So it's an unusual experience to go there. But bless his heart, Brewster is really dedicated to trying to hang on to the World Wide Web as much as possible. So he would be a natural place to try to install things like this. He's also been thoughtful about backup and recovery. So he has backup facilities at, of all places, the Library of Alexandria in Alexandria, Egypt. Now, given all the turmoil and everything else in Egypt, that sounds a little scary. But the operator of the Library of Alexandria, Ismail Sarageldin, is a Renaissance man, and he has somehow managed to avert any serious damage to the library, which is historically important because the first two versions of the Library of Alexandria burned down. So there's this beautiful $50 million building. It's sort of a frustrated cylinder. It's a magnificent place. So, and I think he has at least one other backup facility, but I don't remember where it is. Anybody, do you happen to remember where it is? I want to say something like Singapore or something. I'm not sure. But for sure, if this is going to work right, we're going to have replicated copies of it. This is not too different than a seed bank, you know, where you're trying to maintain biodiversity. What you want here is the ability to recapture the way things worked in the past. Okay, so that's really all I want to try to say about this particular problem, except to say that we have a lot of work to do technically and legally and financially to figure out how to actually sustain this kind of operation. So I want to switch over to the interplanetary internet for a moment. This project got started, it's not a Google project, it got started in 1998 when I visited some friends of mine at the Jet Propulsion Laboratory. Now I want you to try to remember back to 1998. This was the year after the Pathfinder landed on Mars. It was one of the first successful landings after a number of not so successful ones. And so everybody was very excited, especially at JPL. By the way, just to go down a little avenue for a second, one of the big problems if you're working on a project like that is that Mars rotation time is 25 hours instead of 24. And so they call them sols instead of days. And the staff has to be on Mars time because you have to be in sync with when you have communications opportunities between Mars and the surface of Earth and the Deep Space Network. And so I don't envy the people that were running the operations desk because they had to get up at whatever Mars time was. But nonetheless, we were all very excited about the success of that program. And we got to thinking that most of the spacecraft that had been launched over the course of about 50 years or so had used point-to-point radio communication in order to do command and control to get data back. And in 1964, the Deep Space Net was built for that purpose. Big 70-meter dishes in Madrid, Spain, in Australia, and in Goldstone, California, here. So those 70-meter dishes were being used to communicate with spacecraft that were in different parts of the solar system. But that's all we had was point-to-point radio links. And here we were, it's 1998, the dot boom is going like this, and we're sitting here thinking, well, what if we had more rich networking capability? Could we support more complex missions? Could we support multiple orbiters, multiple rovers? Could we have things moving around on the surface? What if we had multiple planets involved? What if we had tandem spacecraft that were building synthetic aperture receivers? There were all kinds of possible architectures of space missions that would benefit from a richer networking environment, just like we benefit from store and forward networking on the internet. So we got to thinking in the context of planned Mars missions. What should we be doing 25 years from then? And it's getting close to 25 years from then now. It's been since 98. It's now what? 17 years, so we got another 8 years to go. At first, we thought we could just use TCP/IP because, after all, it worked on Earth. So why the heck wouldn't it work on Mars? And the answer is it does work on Mars, but it doesn't work between Earth and Mars very well. And we encountered that on the first whiteboard session as we were starting to think about, okay, so what would TCP look like, and what about flow control? How does that work? Well, it's pretty simple, right? You just tell the guy on the other end, I've run out of room, stop sending. Well, that works okay if it's a half a millisecond or a half a second or even a second, because you can buffer that up. But if it's 20 minutes before you even hear that there's a problem, then he's pumping the stuff at you full speed and it's all falling on the ground. So that didn't look too good. Then we looked at the domain name system, and we imagined, okay, you're on Mars, you're trying to resolve a domain name that's on Earth. So you send a DNS lookup, and it goes all the way to Earth, and then they figure it out somehow, and they send it back. 40 minutes have gone by, minimum. And then, of course, the answer's wrong because the IP address that you get has changed in the meantime. So we said, okay, so DNS doesn't look like that's a big win either. So we ended up doing a whole new suite of protocols that we called delay and disruption tolerant networking protocols. Oh, by the way, the disruption was another problem of spatial mechanics. The planets are rotating, and we haven't figured out how to stop that. So if you're on the surface and the planet rotates, you can't talk to it till it comes back around, and the same thing happens with the satellites. So we have an environment where there's variable delay and disruption. And the variable delay is partly a function of planetary motion, not just orbiting, but I mean rotating, but also orbiting. So we developed this new suite of protocols, and interestingly enough, remember this is 1998. So over a 4 or 5 year period, we developed these new things we call bundle protocol because we needed something that sounded like packet but wasn't packet. So bundle. We're not very good at names. We're just engineers. If we had done Kentucky Fried Chicken, we would have called it Hot Dead Birds, and I probably wouldn't sell very well. So in 2004, the first rovers landed, the two rovers, Spirit and Opportunity, and the plan was for the data to be transmitted directly back to Earth at 28.5 kilobits a second. Scientists are griping about what a crappy speed that is. And then it turns out the radios overheat. And so now we have to reduce the duty cycle to keep the radios from harming them, either themselves or anything else that's on board the rovers. And now the scientists are really unhappy. Then somebody says, well, I have an X-band radio on the rovers. Yes, but it can't get all the way back to Earth. Oh. But I have an X-band radio on the orbiters, which were originally designed to map the surface of the planet to figure out where the rover should go. So JPL decided to repurpose the orbiters so they could become store and forward relays. So they used a file delivery protocol that had been developed before the bundle protocol stuff, and basically pushed data up to the orbiters as they came overhead, and then held onto the data in the orbiter until it got to the right place to squirt data back to the Deep Space Network. Now, there were two benefits from this. One of them is it saved the program, maybe we could get data back. But the second one is that you could transmit at 128 kilobits to the orbiters because they were close by. And the orbiters are out of the atmosphere with bigger solar panels. They could transmit at 128 kilobits back to Earth. So we actually got 4 times more data rate by changing to store and forward. So this at least was a demonstration that a store and forward network was a good idea, even if a very small, 2-hop system. So then the Phoenix lander arrived in 2008 at the North Pole of Mars. There was no configuration that would allow it to transmit data directly back to Earth, so they had to use the store and forward system to do that. When the Mars Science Lander arrived a couple of years ago, the same argument was made. It should use the store and forward system for communication. So we got very excited about demonstrating this result. And we have been implementing and developing, and I would say revising the protocols ever since. So at this stage of the game, the bundle protocols are running on board the International Space Station. They are running here on the surface of Earth. They could be run on the rovers, although at this point, since everything is working okay, they don't want to mess anything up. But the proposal right now is to use the new standardized bundle protocols on future space missions. They've been standardized by the Consultative Committee on Space Data Systems. which is made up of all of the spacefaring nations. So they have agreed on this standard for communication. What this means is that even if a spacecraft is launched to do a particular scientific mission, and even if it doesn't actually use these protocols for that mission, if it survives the mission and completes it, it might be repurposed as a node in an interplanetary backbone, which is what you sort of see here in a fanciful way. So we think over the next several decades that we can literally grow an interplanetary backbone mission by mission. So we're not going to go build this giant interplanetary network and hope that somebody will come. That's not the plan. The idea is to simply let it grow naturally as we launch missions around the world or throughout the solar system. Recently, that's last year, we did another test. Oh, I'm sorry, 2 years ago. We did a test from the International Space Station. One of the astronauts, using the bundle protocol, controlled a little rover in Germany as he was driving around on the surface, as if you were emulating an astronaut in orbit around Mars, directly controlling the rovers. You couldn't do that from Earth, right, because of the round-trip time delay. By the time you figured out you'd gone over the cliff, you know, it's too late. So this emulated a more interactive environment. And then last year, there was another very interesting test. The guys at Goddard got an optical transmitter to the moon, running at 600 megabits a second, running the bundle protocols. So we've been able to demonstrate high speed as well as, you know, resistance to or resilience in the face of high and variable delay. So now you can sort of see that we're hoping that this will catch on and that this will become normal for both manned and robotic space missions. But there's one other bit here that I'd like to share with you, and that's the ARPA project to design, not build, but to design a spacecraft to get to the nearest star in 100 years' time. So it's not that 100 years from now, it's more like the spacecraft takes 100 years to get to Alpha Centauri, 4.3 light years away. Now there are some little challenges associated with trying to design a spacecraft that can achieve that. One problem is propulsion. At the present, the propulsion systems that are already available to us would take about 65,000 years to get to Alpha Centauri, which is a little long even for an ARPA project. So it's only 6 times longer than our civilization has existed, right? So we need to do something about that, and the something probably is going to be an ion engine. The problem will be, can we supply it with enough fuel to last at least 100 years? Can we get it up to about 20% the speed of light, and at the 50-year mark, slow down? Because otherwise we'll go blasting through the system at 20% the speed of light and get one picture. There's also a navigational problem, and that is that, you know, the stars are not exactly where they look like, right? Because we're seeing them delayed by the speed of light. So you have to have the spacecraft adjust its trajectory somewhere during mid-course. Now, when we're doing exploration of the solar system, we usually do mid-course corrections by doing, you know, not exactly real time, but I mean, in the middle of the transit, we will send instructions to the spacecraft, and this may be minutes, may even be hours of, you know, delay. But imagine that you have a spacecraft that's a light year away, so it takes a year for the signal to get there, and another year for you to find out what happened. So this is not exactly interactive. The result is that we probably have to do autonomous navigation in that spacecraft. But I think that's possible because we have a pretty good idea of the proper motion of the stars that are within our neighborhood, 10 to 50 light years away. So autonomous navigation will probably solve that problem. And then the final problem is communication. How do you generate a signal from 4 light years away that you can actually detect here? And I'm not expert in all of this, but the first thing that came to mind was laser communication, preferably pulsed femtosecond lasers or attosecond lasers. It turns out that those pulses, you know, if you have a 100-watt transmitter and you compress the signal to 10 to the minus 15 seconds, that's a hell of a big spike. And in theory, you should be able to detect that from quite a distance away, except for one little problem. Even with a laser, a collimated laser, there's going to be beam spread. And by the time you get back to Earth 4 light years away, the signal is probably about as wide as the solar system. So now you know why I need the interplanetary backbone, so I can build a synthetic aperture receiver to reintegrate the signal coming back from Alpha Centauri. One of the physicists came up with another idea. He pointed out to us that, that the sun's gravity bends light and therefore could be used to form an image. You just have to go out to the right focal length. Well, it turns out that the focal length for the sun is only about 55 astronomical units away. That's about 55 billion miles. And we don't have anything that's ever been that far away from Earth. We got the Voyagers, right? They're like about 13 billion miles away. So, and that only took 33 or 34 years to get there. So this would be a great test for the ion engine to try this out to get something at 55 AU away. And then we have to figure out where can we generate a signal that can verify that. So we'll have to send two of them out, one on this side of the sun and one on that side of the sun, and have the signal get bent back by the sun's rays into a focal point. But that might be the best way to communicate without having to build a big synthetic aperture receiver. Well, I won't be around to actually see the fruition of this project, but if you're like me, just being involved in something like this, even at the very beginning, is like being in a science fiction story, except that it isn't science fiction. And the thing that I enjoy the most is sitting around with my colleagues and having serious discussions about how long does it take to get to Alpha Centauri, what's the signal level that we have to deal with, what data rates can we sustain, because you're really doing engineering. And that's all this is. This is, you know what engineering is? It's turning science fiction into reality. That's why I like being an engineer. I'll stop there. I'm happy to do Q&A, and I really appreciate the chance to just meet all of you. Why does it go backwards?
Okay, so we have plenty of time for questions, so we'll take them here, and we can also handle them remotely. And I think we can also handle them over chat for those of you who are on Adobe Connect.
Okay.
So
do you want me to hand microphones around? I can do that.
There are microphones acting.
You can press the button.
Oh, you've got a button. Okay. Yeah. So there was a hand up over here. Where was the hand?
Is there a microphone here? Can you hear me?
Yeah.
I have a question or observation about virtual machines. I believe that IBM and VMware are the main providers of virtual machines today, and they don't emulate everything. They emulate part of the environment, and the real hardware does the rest of the work. And
okay.
so I'm wondering about multiple layers
that
you're going to need. For example, I don't suppose that there's very many Commodore and Radio Shack TRS-80 emulators around, because that hardware is completely incompatible with all current hardware. But 100 years from now, you're going to have at least 6 layers of emulation out there.
Oh, no, not necessarily. Let me argue that we don't necessarily have to have multiple layers of emulation, although I have some stories to tell about exactly that. I think it's possible to have any machine. I mean, look, these are Turing complete, right? So in theory, any machine can emulate any other machine. The problem is getting accurate descriptions of it. For purposes of speed, what you just said is exactly right, that you emulate what you have to and then let the hardware do the rest. But in the worst case, we can run all of it as emulated functionality. The question is, how fast does it run? And what is interesting about all this is that machine speeds have gone up so fast that right now your emulated machines run faster than the ones you're emulating used to. And so you can actually play some of these computer games, and it's more fun now than it was then because it's a lot faster. But points well taken. Back in my salad days, I used to run a business emulation for a company called Carnation. And originally it ran on a 1401. So it was written in autocoder. And IBM, so I started doing this in the mid-60s. So first it was on a 1401. Then the 1965 comes along and the 360s come out. And so now they're emulating the 1401 on the 360. And so we still run the same program. And then the 360 model something or other, I don't know, 50 or something, gets replaced with the model 30, and it's emulating the model 50, emulating the 1401. And we started running through several layers, exactly as you're describing. until finally we decided that, you know, every time we did it, something would break, right? Something wouldn't work quite right. And every year it was different. And so it was always a challenge to run this thing. So we finally rewrote it in a much newer language called Fortran. And, and that compiled on all the machines that we were running this thing on. So yeah, emulation is possible, but it's also painful. Okay, yes, sir. Well, so what Satya has done is describe in XML the actual hardware that it's trying to emulate. So the theory there is that we should be able to correctly interpret the XML over periods of time. We may end up having to preserve the XML interpreter in an emulated environment in order to figure. I mean, you can see how this could get complicated. Yeah, especially XML. Yes, so maybe we'll have to do an HTML5 version of this. So, you know, you're quite right that this, even with our effort to preserve stuff, we may still have to do some additional emulations or re-implement emulations in order to keep this in perpetuity. With regard to the snapshots and the size of the virtual machines, I think the way this works is that he's keeping just the operating system image and the application image. Now, you're right that that could still be pretty big. Ironically, we've been able to keep up with a lot of the memory demand, and we may be able to keep, we're far from running out of storage density, especially if we start getting into atomic level storage or even cellular, you know, DNA types of storage. I know that you can't always predict the future based on the past, but I did have an experience recently that sort of emphasized for me the storage density and cost curve. So I bought a 3 terabyte disk drive for something like $150 recently, and every time I say that, somebody says, mine only cost $100 and you went to the wrong store. But I remember buying a 10 megabyte disk drive in 1979. It was for an Apple II Plus. And it was the size of a shoebox, and it cost $1,000, $1979. So as I was thinking about the difference here, I decided to do the math. I said, what if I tried to buy a terabyte of memory in 1979 at 1979 prices? And if you do the arithmetic, it's $100 million. So, you know, clearly, you know, things have changed. I didn't have $100 million back then, and to be honest, I don't have $100 million now either. But if I had had $100 million in 1979, I'm pretty sure my wife wouldn't let me spend it on disk drives. Besides which, I didn't do the volume calculation, but I just wonder, $100 million worth of 10 megabyte disk drives probably would have been not only fill up a lot of space, but I wonder how much power I haven't done that one. That would be interesting to see how much power would have been required for a terabyte of disk drives in 1979. Probably need a small nuclear power plant in the backyard. But those are very good questions. Let me get one in the back and then one here.
So I'm Ian Jones from Oracle Labs. What aspect of the new protocol, the store and forward protocol that you described, would be appropriate to actually upgrade our network systems here now?
I'm sorry, what aspect of the protocols?
Would help us upgrade our network systems?
Oh, you mean, yeah, so could we use this stuff now? And the answer is yes. Let me tell you what happened. DARPA originally helped sponsor the interplanetary backbone work. It was before NASA got involved. And something like 10 years later, after the stuff is working, we went back to DARPA and we said, we've been thinking about tactical communication environments, and we're thinking about the brittle nature of TCP/IP in environments where there is a lot of data loss, or maybe even some variable delay, but mostly data loss. And so we think that these interplanetary protocols might be good for tactical communication. And so DARPA, in its usual style, says, okay, prove it. And so they funded some tests where we went out to Fort A.P. Hill in Virginia, and we had the Marine Corps helping us with this. So we did 2 simultaneous convoy emulations where the convoys are moving into a new map area and they're trying to download new map zones over a satellite link. And we did one with the TCP IP thing, and the other one we did with the bundle protocols. And because memory is in the network, which we would not have done, we didn't do with TCP IP because memory was too expensive back then. We were also able to store cached information from the map. And so what happened is that we got 3 times as much data through the bundle protocol system, partly because we didn't rely on an end-to-end link being present at all times. We only had to hang on to data temporarily until a link came back up we could relay further. So it actually looks like you would have a more resilient system if you could run the bundle protocols in lieu of, it'll run on top of TCP if you wanted to, even if TCP breaks, the bundle guy can recover. So we have implementations. Oh, that means, am I supposed to roll up into that thing with it? So we have implementations of the bundle protocols for the Raspberry Pi and for Android. It's open source. It's available on SourceForge. So you get Linux copies and Android and some others. So we're hoping, frankly, that the maker people will see an opportunity to just try this stuff out. And we'll see whether or not it catches on. But thanks. It's a good question. Yes, sir. Where? I thought it was over here. Hmm.
Yeah, we're getting this thing right. Yeah. Okay.
Yeah.
A couple things. Yeah, I had actually 2 things, and he covered sort of part of my question. But and then he asked the question there about the all those VMs out there. That's all handled by a thing called deduplication. You know, where you have like a zillion different things, and that same operating system is used by 1,000 of them. So then you only store 1 copy.
Oh, you only have to store the one. Well, the question is whether you can break. Can you break off the VM description from the operating system image on that VM? I think the answer is yes. You could do that.
I mean, just at the bit levels, you can do it with the bit deduplication.
Yeah.
But I had a question on the bundle protocol. Are there any downsides to in terms of performance or anything to the bundle protocol?
Well, the headers are bigger, and we use this 2-stage lookup arrangement. Here's the problem. If you're on Mars and you're trying to communicate with something on Earth, doing a DNS lookup doesn't make any sense. But what we did was, so we decided the addressing structure actually has to help you figure out which planet you're supposed to go to first. And then after you get to the right planet or spacecraft, then you do the local lookup to figure out exactly what's the address of the device on board that spacecraft or on that planet. So the headers are bigger in that respect. We have actually tested this stuff in environments where we have very high data rates. And I'm satisfied that we can do interactive voice and video using the bundle protocols, despite the fact that the headers are bigger, as long as we're operating at high enough data rates. Now, in the environment of RF, the data rates tend to get lower and lower because of the R-squared drop-off of signal levels in deep space. But with the optical signals, you know, we're starting at a much higher data rate. So I wouldn't for a moment suggest to you that there is no downside. But I will say that as we move into these higher speed regimes, for the same reason that internet protocols were useless for certain things until the speeds got up high enough, the same thing will probably be true for space communications. And certainly, the thing that we were particularly driven by is the possibility of local networking going on the surface of a planet or in the neighborhood of the planet far away from Earth, where you don't want to go relaying all the way back and forth to Earth, which you would typically have to do if you were using just the deep space network. So at this stage of the game, I am more confident that we have useful capability in spite of the fact that some of the mechanisms are bigger. And there's a lot of resilience built into these things. There's retransmission capability, hop by hop, which we don't do in the internet. Yes, sir.
So Vint, this is back on the digital Vellum idea. So when we think of apps as something that we could load onto a PC, the thought of being able to sort of encapsulate all of that stuff is sort of a tractable thought. But now in the world of distributed computing, where an app is some combination of something that runs on my phone and a companion web service that's changing hour by hour, how do we get our arms around that as an app?
Yeah, that's a really good question, because we're in environments now where there's a lot of things all happening at the same time and not under our control, and we don't even have the ability to capture all of that because it's, as you say, it's operated by different parties. I haven't actually thought hard about the preservation of the app environment. I'd have to sit down and figure out whether or not you can take that problem and somehow distort it enough to use the trick that Satya is suggesting. We could certainly make the separate pieces work that way, right? You could emulate the app running on the mobile with the same trick as the virtual machine idea, and the server could be, you could do the same thing with. So I don't know whether that's sufficient. It certainly does not mean you're emulating the experience, because the experience is you're mobile and you're moving around, you have a device you can use. I don't know whether we could make handheld virtual machine emulator mumble. So
then you also have to recreate the DNS context for resolving the
yeah,
addresses.
okay, so this is, no, this is really the more important point, which is that the rest of the ecosystem that makes the World Wide Web work may be really, really hard to reproduce. Which is why Satya very clearly says that this idea he has works for certain cases, but the link rot problem, the disappearance of links because somebody didn't renew their domain name, is a real problem. It's a serious issue for online publication, because if all you have is an HTTP string, you're going to get 404, file not found or page not found increasingly over time. And so those of us who care about digital preservation I am convinced, I won't speak for anybody else, but I am convinced that domain names are the wrong mechanism and the URLs are the wrong mechanism for long-term storage. There's an alternative idea for identifying digital objects, something that Bob Kahn has worked on at CNRI, called the digital object architecture. And he has arbitrary, more or less uninterpreted, and never reused strings to attach to a digital object. You still need to do resolution. You have to have resolution over the course of a long period of time. You need to have repositories that will hold the digital objects, and the lookups would resolve to them. But you have to decide that you want to create a sustainable storage system like that, which is not subject to the whims of domain name registration. So, I mean, unless we start thinking about the problems that you're thinking of, and thinking in making ourselves think in the long term, I don't think we will invent the kinds of mechanisms, ecosystem, and infrastructure that's necessary to preserve all of that.
I wanted to follow on Bob's question, because a web application isn't an application. It's a series of calls to a bunch of different applications running on a bunch of different machines. One is delivering images, one is delivering a feed, another one is doing the e-commerce for you.
Yes,
so,
and it all looks like it's just one cached thing, but it isn't, as you say. It's coming from all over everywhere.
Right.
So the problem there is trying to reproduce that experience requires you to hold everything, which is what Brewster tries to do. His Wayback Machine is actually remarkably successful at giving you a sense of what was there, even though nobody in his right mind, I think, would argue that we can preserve the entire World Wide Web. Even the search tools that we do at Google are not historical, right? They are simply the latest image of that we could see that was on the World Wide Web. And so if you wanted to find something that you saw last Tuesday, it may not be there anymore because somebody changed the web page or took it away. And we're not coping with that.
It's much better with static pages than with data-driven websites.
Yes, well, yes. It used to be, by the way, this is the other big problem. We didn't mention security, but it's funny, when HTML was just a formatting language, and all you were getting were images and text and layout, that was a fairly benign environment. Now you download executable software or interpretable software, and hence malware, and hence a far more dangerous environment. So we've invented our way into danger, and we have to find a way to invent our way out of it again. This nice lady should have a shot at it. Madame?
Yeah, this is also related. So you talked about the storage challenges for this
For all
software
of it, all this
museum.
thing, yeah.
Yeah, I was wondering, coming from Google, if you would like to comment on the challenge of searching through this data and also classifying all these new kind of.
So the question is, what about not only the amount of data, but what about searching to find that data? This is an interesting mixture of things. Tim Berners-Lee talks about deep linking, and one of the things that he's getting at is figuring out how to characterize stuff which is not written in HTML or HTML5 or XML. There must be an awful lot of data that's in the internet that is not visible to a search engine. And I always think about it as like dark matter in the universe. You know, we know it's there, but we can't see it. And there's a lot of stuff on the internet that has that characteristic. Figuring out how to get it to self-describe what's in it, as opposed to some, person sitting down manually trying to describe this stuff, is a big challenge, and it implies looking for ontologies that would allow you to characterize what the contents are of objects that are not expressed in HTML or XML or HTML5 or whatever comes next. Again, we don't have a regime and a set of tools that automatically do that. I think if there were serious demand for this, that we could invent something. It makes me think of what happened in the early days of World Wide Web. People were actually writing HTML commands using text editors. And eventually they got tired of that, and we wrote programs that let you drag and drop and format things in a more convenient way. It could be that the production of content could be done with tools that automatically do indexing and description. I'm reminded of something at the National Library of Medicine. There are human beings who read technical documents that are published in the medical literature, and then they use what's called the medical subject headings, which is a controlled vocabulary, to describe what they read. And then they say to you, if you will just search using the medical subject heading terms, then you have a high probability of finding the stuff that we have described for you, which is okay for doctors and other people who are comfortable with that lingo. But if you wanted to look up something about stomach ache, the first thing that comes to your mind is probably not gastrointestinal distress. And you'd type stomach ache, and nobody would find anything unless that got translated into gastrointestinal distress, which is what Don Lindbergh, the head of the Library of Medicine, did. He has this sort of a dictionary which he calls the Meta-Thesaurus, and he has a dinosaur in the front of the booklet. And it basically translates from conventional terms that we would use to describe medical conditions and the formal definitions, so you can find documents that are appropriately indexed. So you could conceivably do what you're suggesting, and I suggest we should be doing what you're suggesting. Otherwise, we'll lose all knowledge of all that data, especially scientific data that might have been collected that we want to re-examine again later on. Yes, sir.
So I also I once wrote about this exactly problem of meta-knowledge, how to storage this through time. And it also relates, for example, if we get, for example, the Mayans, and
yes,
with their knowledge, we have a big difficulty to understand what
were they trying to tell us?
Yeah.
Yes.
So do you think it's a wicked problem to storage like the internet, as you said, or it could be solved?
Oh, I think that we have a big challenge if we wanted to store everything, I think that's very hard. Although I have to tell you, Larry and Sergey believe that if you can store everything, you should, on the grounds that you don't know what's important. And a very interesting little scenario to go all the way back to Doris Kearns Goodwin again. I was speaking to a room of librarians, and one young man, hearing about this concern, jumped up and said, "This is not a problem. If it's important, somebody will transform it into the newer formats, and if it isn't important, nobody will care." It took me a half an hour to get the librarians off the ceiling because they said, "You don't know what's important for 100 years or more. Sometimes perspective tells you what's important. Sometimes a new physics discovery says, wow, I should go back and re-examine the data that they collected 100 years ago and compare my results." And so if we don't preserve our ability to correctly interpret that data, we won't be able to do that. And the metadata is really important. I have numbers, 16. Great. Yeah, was that centigrade or Fahrenheit? Was that pounds of pressure? Was it something else? So just having a bunch of numbers doesn't do you any good, which is why the ability to identify the data and the metadata that goes with it, calibration of instruments, conditions under which the data was collected, all that stuff is really critical. One more.
My question is basically like, how can we do this, for example, for humankind 1,000 years after? So how can they understand the internet network that we perceive today?
Well, I don't know whether they actually need to. It might be interesting to experience the internet, just like it's kind of fun to play Zork, or and some people remember that. Or was it? What was the other one? The original one that they did at Xerox PARC. It was either not Dungeons and Dragons. No, I'm sorry. This is the old guys talking about stuff. It was Colossal Cave, and it might have had another name as well. Anyway, we could still play those games. Yeah. It's the one. It was Plug and X Y Z Z Y and all those special commands. Yeah. Anyway, so we may not be able to actually reproduce the experience of the internet, but we might at least be able to preserve enough of its content to be useful in the future. And that's my aspiration is to do at least that much.
Okay, thank you so much. Let's give Vint a big
Thank
applause.
You very much.
And
Appreciate that. Thank you.